can answer this question with very little difficulty. I'm going to have a roller coaster track, something like this, where we have say a roller coaster car that will be placed at the top of this track and released. And I'm interested in that location of the track. Now let's make some decisions real quick about the size and structure here. So I think it appropriate that we have some kind of necessary measurements. So I'm going to make a agreed upon baseline that we're all going to use. Is that an okay baseline for us to use down here? We can choose any baseline we like, but I think that would be good. I'd give measurements based on that. Let's say that we are beginning 50 meters above the top of the reference level, and that this is a 15 meter radius. All good? Let's assume that this is set up in magical physics land. So no friction, air resistance, sound, nothing. We're just dealing with conservative forces. So could you tell me, when the car makes it to the top of the track, what is the normal force acting on the car? Now, I'm asking a question I believe you should be able to solve with the information you got yesterday and your prior knowledge of physics that we've used for the last couple tests. If you don't know what I'm asking you to do, I can break this up for you in two parts, and I will write them in code on the side of the paper or on the side of the board. But the rest of you who think you know what to do, get started. And I'll say it again, this is not a quiz, but it could be tomorrow's quiz. All right, look, I don't have time for you guys to be all this slow about it. Who has cracked the code and figured out the first thing to do? Did you find it? Yes. How fast is the car going when it makes it up to the top of the track? 20 meters per second. Now look, if we're all good with that, I'm going to move on. But if somebody has difficulty with that and needs help, you're going to have to answer several questions for me. All right. Can you tell me the type of energy the car has when it's being released from the top of the track? And what's the equation for gravitational potential energy? That's it. We're done. That's the equation for gravitational potential energy, mgh minus h naught. All right, when we're at the top of the loop, what kind of energy does the car have? All right, what is the height of the car when it's at the top of the loop? All right, and we also have kinetic. How do I calculate kinetic energy? All right, well, other people help, so I'm going to put it down. Are there anything but conservative forces acting on the car during its trip around the track? So this amount of energy at both states has to be the same. That's it. Solve for V. The M's cancel, and the G's do not. Remember, Simon. If you watch the 5th period video, it's pretty funny. So we cancel out all the M's. We get 500 minus 300 equals 1/2 V squared. So V is the root of 400. So V is 20 meters per second. All right, so we have successfully found the velocity at the top. Next, you need to use net force. That's the next part of this, is using net force. How many forces are acting on the car when it's at the top of the track? I'm sorry, when it's at the top of the loop? This should not be tough. Name one force acting on the car at the top of the loop. Okay, we've nailed the easy one, gravity. All right, let's start our list of contact forces. Is the car in contact with anything? Yes. What? Track. I actually had somebody last class period ask, is the normal force always down? And I really, really wanted to hurt that person, but I patiently answered the person's question. Now, are there any other forces acting on the car? Is there a cable connected to it? Is there friction, air resistance, anything like that? No, so this is it. And we've done this problem before, so you guys having difficulty makes me sad. This will be on your next test. So I see two forces. So net force equals MAC. Why do I know it's MAC? It's traveling in a circle. None of this changes just because we're dealing with energy. Forces are still involved. They're intimately involved. So, not that kind of intimately. By the way, this is not the question I want you to answer. I have something else you need to answer. We're just getting started. Now, you can get an answer for this, but it's not going to be in newtons because I didn't give you a mass of the car. But that just means you're going to have an answer that has M in it, correct? So if you've done this correctly, excuse me. Oh, thank you. You get to a point like this, correct? If I told you the cars were 100 kilograms, you could give me a value for the normal force in newtons. This was not the question I wanted to ask. This was just reminding you that you know other things, or you need to. Because the question I'm actually going to ask is, if I want to make sure the car makes it through the loop, where do I have to start the car? Well, you remember that this is a conditional problem, and there is a minimum speed the car must have at the top of the loop. Do you remember that from a couple weeks ago? So I'm asking the same question I just asked, or at least your work is more or less the same work we just did. But I want you to work this problem backwards. Where? Along the track. Well, let me just ask it different. How high do I have to start the car on the track in order to ensure the car makes it around the loop without losing contact? What you have to do is here, in front of you. You just have to remember what we did. And by the way, I do appreciate the fact that nobody pointed out my bad algebra. So thank you so much. I would have thought Matthias would have already done me about it. Don't you mean there's a negative sign there? Yes, I just forgot. Get to it. I asked a question. I'm going to pick on one of you. You have to do this problem in the opposite order, by the way. Meaning start with net force and find the velocity, the minimum velocity. I did wait patiently, a solid 3 or 4 minutes, and I was really hopeful that maybe this class would be, would be able to jump right on it. But I see you struggle, and we have more to do. So I'm going to lead this a little bit different, but I have to begin to expect you to remember things, right? So, net force equals MAC. We're starting here. I want to find the minimum speed necessary to successfully make it through the loop. And I'll recall that there are two forces that act on the car to help it turn successfully through the loop. Now, we had no trouble this last time. There's plenty of velocity to see us through the loop. But this time, as I look at this, mg is a fixed value as I go through the loop. But remember, v can get bigger, and if it does, n gets bigger. Right? The faster the car goes, the more the track pushes on it. But if I start making v smaller, the track pushes less and less. The minimum occurs when the normal force goes to 0. Seeing that normal force in some of your equations made me sad. But this is when this is our threshold. This is when we're not touching the track any longer. Now from there, I can figure out quite quickly what the velocity is going to be, what the minimum velocity is going to be. And in fact, I'm going to work this problem without any numbers for now because there's no reason. No reason to put them in there. I mean, already I'm seeing this come together. I'm just going to leave it just like that for the time being. And the reason I'm going to leave it just like that is I'm looking at the future. Are you all listening to me? Or are you just writing things down? I'm looking to the future. And the future of this problem is I'm going to use energy to determine how far up the track I want to release the cars. I know that right now where the cars are, they have kinetic energy and they have gravitational potential energy. Leaving this as v squared works for me because kinetic energy is v squared, right? No reason to put the square root down if I'm just going to square it again. Which makes me remember that I will have two forms of energy when I'm there. Does everybody understand why I put 2r there and not 30? Because I have an r here and I'm going to put a 2r there. Why not? I'm going to work the whole problem in these variables. I'll put the numbers in later. We all good so far? This has to equal mg h minus h naught. We are trying to figure out where to start the cars. So, again, I don't really need the mass of the cars for this. I would need the mass of the cars if I wanted to know how much force there was. I would need the mass of the cars if I wanted to know how much energy there was. But for figuring out something in between, doesn't look like I need the mass. So I'll get g h minus h naught equals 1/2 rg plus 2 rg. Any question about where I got any of that? Are you sure? Make sure you're paying attention. If tomorrow you walk in and I say prepare for a quiz, are you going to be okay? So look around the room. Yes? I just rearranged these letters and put the 2 as the coefficient out front. Is that okay? All right. Now, there's only a couple things left to do. Like I can add these together, correct? I can also cancel out all the g's. Do you see that too? So let's get rid of all those g's because we don't need them. There's one in every term. And 1/2 plus 2 is 1/2 plus 4/2, which is 5/2. So this is 5/2 r is h minus h naught. That's the answer. That's where I better start the cars. R is 15, by the way. So if you want a number, now you can get a number. I'd also point out, though, it's 5/2 r for every looped track in the world, right? If you want to make a looped track, you have to start your cars 5/2 r above the ground. Right? We have solved it for every looped track. Now, that's for a circular loop and assuming that we're in special magic physics land. Right? We understand that we're probably going to have to start it higher than this. Do you understand what I'm saying? All right. How many minutos do I have? I have enough. I don't want to do this problem again. What I want you to know is that it's super easy for me to change this problem but tell you it's the same problem. And I know you hate it when I do that kind of stuff, but here's me changing the problem and telling you it's the same problem. What's the highest I can start the car and not have them jump off the track? I'm not working this problem. I'm telling you that this is, to me, the same problem, the same kind of problem. And do you remember doing this problem before? So we're not going to work it, but I think maybe if you want some practice, not a bad place to look. And the other one, we had to start the car higher than this. This is telling us that we better not start it too high or the car will be going too fast. And instead of traveling in a circle, it will become a projectile. Right? We're combining what we did in the first in Unit 2 with Unit 3. That's all this is. But I want to add to the body of knowledge today, or try to. And today is going to be tough for some of you, and I'm okay with it. You see, a spring provides a conservative force, which suggests to me that we should be able to use a spring to store energy. That's not a surprise. Who's ever shot a bow and arrow? Okay, so all 5 of you. Yes, the bow stored elastic potential energy, which it delivered to the arrow. I guess we'll have to maybe go back a couple extra years. How many of you had one of those silly little cars that where you pull it back, you could let it go, and it zipped forward? Okay, what do you think was in there? It was a silly little spring. You pulled it back, you wound up the spring. When you let it go, the spring pushed the car forward. Pinball, you pull the plunger and let it go, the ball goes shooting up the thing, right? Same idea, you're storing the energy in a spring. The issue for us, and something that I need to clarify, is that calculating the work done compressing the spring will tell us how much elastic potential energy the spring can hold. So if I push the box against the spring, like so, and compress the spring a displacement delta x, say for a spring of spring constant k, I'd like to know how much work is done. Because I know potential energy is equal to minus the work done by a conservative force. So as I push on the box, I do work on the box, and the spring also does work on the box. Does that make sense? I'm interested in the energy stored in the spring, which is the work done by the spring. Now, here's where we have a problem. This is going to be of no use to us, because as I compress a spring, the force required to continue to compress it increases. If you'll recall, there's Hooke's law, which says that the more I compress the spring, the more force that's required. This is not a constant force. So you'll have to integrate in order to find our answer. Now, this is one of those things where I am not expecting you guys to be good at this. We have lots of semester to go into this, but I do need you to get a few things written down real quick. First, this is called a linear spring. And I hope you understand why. Hooke's law is a linear equation. If I double the displacement, it requires twice as much force. That's a linear relationship, right? You can see y equals mx plus b in the equation, right? Linear springs. There are lots of springs in this world that are not linear. There are springs where if you double the displacement, the amount of force goes up by a factor of 4 because it's a quadratic spring. So the Hooke's law for that would be F equals kx squared, right? There's lots of different versions of this. So, and they've given these on the exam for years because there are different kinds of springs. And so they will give you a problem in which the work done might need to be calculated using an integral because you have something like this where the energy stored is not based on a constant force. The process will be the same. We're going to start with linear ones and we'll work up examples next semester and slowly add them so that you can become proficient. But let's actually look at what it would take to find out how much elastic potential energy there is in the spring by using the standard definition. The standard definition of work. I'm taking the dot product part out of it, but this is what we're going to do. And here's the deal. We're going to assume that the spring started at its natural length uncompressed, which means we're going to start with the spring at a displacement of 0 and displace it to some amount delta x. Now, if you don't like the fact that there's going to be a delta x in our limit, you could just put d there if you'd like. But I'd like my answer to be in the same context as Hooke's law. Does that make sense to all of you? All right. This process isn't hard. The first thing I'm going to do is recognize that I'm not talking about the force that I apply. I'm talking about the force the spring applies. So we're looking at a cosine of 180 already, right? The spring is pushing to the left, but the force from the spring is to the left, but we're displacing it to the right. Does that make sense? And I'm going to drop in just the kx part, because the negative sign there is telling me that the spring is pushing to the left while I move the box to the right. That's what the negative tells me. But I already know that. I'm absorbing it into the cosine. Everybody good? So that means my integral from 0 to delta x of kx dx. That's how much work will be done compressing the spring. Now, I've said this before, I'm saying it again. The process of doing an integral is just a couple of steps. I'm not going to write out these steps basically because we're going to run out of time. But the first step is just to find the antiderivative of your integrand. This is the integrand. I want to find the antiderivative of that formula with respect to whatever this variable is, which means that variable is the important one. Anything else can be considered a constant. You guys understand that? I'm giving you information. I'd encourage you, if you don't know that, to write it down. Again, the thing that I have this caret on, this is called the integrand. I want to find the antiderivative of the integrand with respect to whatever variable is after the d. That means that variable is important and the other one is a constant. Constants can be brought right out front of my integral because they are unimportant. If they're being multiplied together, I can just bring it out front. Now I have to find the antiderivative of x with respect to x. Not challenging. That's a polynomial. X is actually x to the 1 power. And I can use my polynomial rule to find the antiderivative. If I remember that rule, I have to add 1 to the exponent and divide by the new exponent. Sorry, I'm forgetting to write the cosine of 180 out here. Cosine of 180 here. So I'm going to add 1 to the exponent and divide by the new exponent. I'm going to remember that I have limits. I have to put my limits in. And I'm going to just go ahead and say this is negative 1. All right, step 1 of doing an integral is done. I found the antiderivative. Step 2 of doing an integral is I put in the top limit, and then I put a negative sign, and I put in the bottom limit. Top limit, delta x squared, minus bottom limit, 0 squared, over 2, all times negative 1. Now, I'm done. I have successfully integrated my expression for force with respect to distance. So now I have to clean this up, and I hope you'll know this is 0. I'm going to have a negative, and this all looks like negative 1/2 k delta x squared. The work done by the spring while it was being compressed. Everything okay? Now, it wouldn't have mattered whether we pulled the spring out or pushed the spring in. The same amount of work would be done. It would have flipped just the direction of the force and the displacement. Hello, Mr. Lewandowski.
I'll wait till you know.
Okay. Now, remember, we want how much elastic potential energy there is. So if you didn't follow all of this, and what Mr. Lewandowski would call this is nerd speak. He thinks this is all nerdy stuff, and he might be right, but nerds rule the world. Well, not this nerd. There's probably some nerd that rules the world, but it's not this one. So all of this is what I'm going to need you guys to become proficient in. But we have 4 months to do so. The result is actually what I need you to be using right now, because the elastic potential energy is just the opposite of this. So get rid of that negative sign. And that's what we will use as an expression for elastic potential energy. Now, this just adds one more to our list of possible energies. And when we start considering that, we only have three, right? We've got elastic potential energy, gravitational potential energy, and, well, that's it, right? Kinetic energy's out there. But that's all we're going to use right now when we deal with conservation of energy. Next semester, we're going to add some to that list, but right now, this is it. And again, this is a potential energy, which means it is derived from the interaction between your object and something else. In this case, it's not just the spring. It's the fact that there's something that holds the spring still, right? That's the interaction. It's interacting with all of that. So as I said before, all potential energies have to be stated that they occur due to the interaction between two or more objects. It's never by itself. Kinetic energy, a single object can have, but potential energy requires a system. In this case, it would be the block spring system. So I hope you can imagine the exact next place we have to go. You understand that if we're going to look at what the possibilities are, the next possibilities have to be problems in which we take the block, the spring, and then, something like that. Pull back the block against the spring. How far along the ramp does the block go? You can imagine that, right? Or how about not even that? How many of you have ridden Hulk or I don't know, Rock and Roller Coaster? All right, so even Cheetah Hunt to a certain degree. Hulk and Rock and Roller Coaster use a pneumatic launch system like aircraft carriers, and Cheetah Hunt uses a linear motor to propel the carts. But if you were building one for a kid to play with, then you could just have a roller coaster that has its launch start from a spring. Anybody know why we don't do this with humans? Remember the way a spring works. If you pull back the cars, Hooke's law tells you that the more you pull it back, the more force it takes, right? Well, the reverse of that is also true. When you release the cars, they experience the maximum amount of force first. So when you set that equal to MA, you oftentimes create accelerations that are, not survivable by humans. So we don't do it that way because it tends to break necks and stuff like that.